بل أحياء عند ربهم يرزقون. نترحم على روح الشهيد سامي أبو دياك الذي ارتقى فجر اليوم في سجون الاحتلال الغاشم. نقف دقيقة صمت ونقرأ الفاتحة على روحه. شكراً. نبدأ هذه الجلسة للمتحدثين الرئيسيين. We have two speakers today in this session. Professor Hans Ruschwe. Hans Ruschwe was born in 1937 in Germany, engineer education in the Aachen University, Department of Aeronautic, promotion to doctor engineer at 1974 with wind slots at circular cylinders in natural wind at high Reynolds numbers. Habilitation in the field of wind engineering in 1985, professor for wind engineering at the Aachen University since 1985, special research work in the field of wind-induced vibrations. In 1996, founding the own consulting company, Ruschwe Consult GmbH in Aachen, Germany, establishing an own boundary layer wind tunnel, consulting for wind actions at buildings and structures, national and international. The title of the paper of Professor Hans is Wind Actions at Buildings and Structures. Please, Professor Hans.
So, ladies and gentlemen, I want to introduce a little bit more for me. At first, I'm very proud that you have invited me to speak to you, to your very honorable audience. And I would say that I was invited by, I think, by the action of Mr. Amro. He knows me very well, not personally, but by my literature, he told me. And I myself, I'm more as an aeronautical engineer. And when I was a student, then the chief engineer asked me for a problem arised in England. Cooling towers fall down by the wind. 3 cooling towers of a group of 8 cooling towers. Natural draft cooling towers is 200 meters high cooling towers. And the chief engineer asked me, Ruschwe, you are an aeronautical engineer, you know something about the flow. You can look why is this failure occurred. Please make a wind tunnel test. And this was my wind tunnel test for civil engineering structures. And that was the key that I found out that the wind load on civil engineering structures is a very interesting field. And I stayed there and made more and more and more in this field. So I'm more or less an expert in this point. And I'm very happy to be here and will you tell something about my field. At first I would say the wind loads on buildings, high wind loads, is not the topic of my speech because I have learned you have not so high winds in Palestine, but the wind effect is also at low winds. And this I will speak about. This is a problem of wind-induced vibrations. Yeah, this is the table. The problem what I speak about is gust actions, vortex shedding, galloping, interference galloping, and rain, wind-induced vibrations. And at first, I will say gust actions are a common phenomenon, and this can be calculated by codes, wind codes. These are standard in every country, and this is based on Davenport. Davenport is a very known person in that field. He developed a calculation method for gust wind actions. I will not speak about this. This is well known, and you can read it in the codes and in the literature. I will speak about, come on. I will speak first about vortex-induced vibrations. The vortex-induced vibrations is connected to the famous person von Karman. Von Karman he investigated the vortex separation, the regular vortex separation on a cylinder. And it is well known that behind the cylinder there is a so-called vortex strait. And von Karman investigated this strait. So at the end of the last World War, Karman was in America, came back to Germany and to a conference. And the people speaking about vortex shedding. And von Karman said, "Why do you discuss this problem? I have solved it." But he has solved the strait, but he has not solved the exciting forces. Therefore, this discussion is still going on, how to calculate the crosswind vibrations on stacks, antenna masts, bridges, slender structures. So I will speak about this. One calculation procedure is very successfully applied in Europe. This is called the correlation length method. This is based on theory made by Vickery, made by other persons, and I have added the correlation lengths, and therefore the method is called correlation length method. I will explain very briefly what it is. The basic of the exciting force is given by an exciting force coefficient. The vortex shedding causes exciting forces. Some people speak about aerodynamic damping. This is not correct. The correct situation is exciting force. And the exciting force produces resonance responses. And this can be applied to cylinders, to stacks, rectangular beams, antenna masts, bridge decks, hangars, slender lattice girders, and turbine masts, and so on, and also on curved elements like bridges. This is a sketch, what you can see here. This is simple case. What? Is the pointer here? Doesn't work? On the left side, you see the single stack that is a chimney. The chimney may have a second mode. You can calculate this procedure also for this. Or antenna masts, mostly they have a cylinder on the top. Bridge hangers, when the very slender structures can be calculated by this method. Or a sign, billboard on the left side, lower side, can be used, or two chimney closed together, and trusswork members can be handled by this, and also wind turbine masts. So it is a universal procedure which can be used. The problem is the characteristic of the exciting force. the correlation, the length method based on the following effect. If the stack left figure is stable, it's not moving, then you have an exciting force. You see it on the left side, and it is not uniformly distributed. It has a similar shape as you can see there, and the integral length, L, is called correlation length. If the stack is moving, vibrating, then the absolute value does not increase, but the length is increased. What is the reason? There is a synchronization effect called locking in. This locking in effect increases the correlation length, and this is a physical phenomena. So, and this correlation length is shown here on the left side on the diagram. On the axis, you see the amplitude, y over d, and on the ordinate, you see L, the correlation length, normalized by the diameter. You see an increase with vibration. The formula is not of interest here. So the increase, have in mind, you start with 6 and you end at 12 approximately. Longer than 12 we have not observed in our tests. So this is the, sorry, back again. This is a formula for the calculation. I will not explain the whole formula. The only point I will explain the KW. This is the effect correlation length factor. This increases with the amplitude. It's a function of the amplitude. That means this, to handle this formula, you start with an assumption of KW, then you calculate the amplitude, and then you see, is the amplitude larger or lower than you have assumed? If it is larger, they go back with a higher value of KW and make the calculation again. That is an iterative process. And it is seen that you need not more than 3 steps. 2 or 3 steps, then you come to the end. Very simple to handle. The other values are more or less constant depending on the structure. Now, come on. Yeah, the coaching, I explained, it requires an iterative handling. Okay. So model tests show that the locking in effect is limited to a value KW of 0.6. That is the maximum we have observed. So you can use an approximation in the first step to use 0.6 for KW. Then you have a value which you can handle, that you can see. Sorry. Come on. So, this is important. The left diagram is very important. On the abscissa, you have the Scruton number. The Scruton number was called earlier times mass damping parameter. There is a mass and the damping included. This is a constant for each structure. And on the ordinate, you have the amplitude, y over b. B is the diameter or the length or the crosswind dimensions. And on the left diagram, you see on this is the black points. The black points is a result of the correlation length method, the calculation. And the crosses, the small crosses you see there, these are full-scale measurements. And you see that the full scale more or less is below the calculation, so the calculation is more or less on the safe side, very close to the reality. The red curve is from Vickery and is related to the subcritical Reynolds number. Subcritical Reynolds number is a theoretical point, is not of interest in the practical application. Stacks and tandem mass and so are always in the supercritical or transcritical range, so the black dots and the crosses are very important. On the rest side, you see an investigations on a bridge hanger. The bridge hanger was not a cylinder, was a cross. You see it on the right side there, 300 millimeter, and there is in the middle a point, a black point. This is calculated by the method. The cross is a model test, and the curve is a full-scale measurement. So you see, the maximum value is very close together. Now I show you a video of a crosswind vibration of a big stack. This stack is in Netherlands, 2 meters approximately diameter, 70 meter high. And you see a big vibration, another view of the same stack. And this occurred at 7 meters per second wind. Low wind. On the Earth, you have not a feeling that there is wind, but it was vibrating. This stack received later on a dynamic vibration absorber in order to reduce. So, okay, next one. So, the next point I speak about is the interference galloping. Interference galloping is called if you have two stacks close together. And there was an observation of large amplitudes of stacks close together or cables, parallel cables, and in heat exchanger was the same problem. And nobody knows why do they vibrate such a large amplitude. And we made model tests in the wind tunnel and found out that for the following thing happens. Phase 1, phase 2, 2 cylinders in a row. The phase 1, nothing happens. The second cylinder is in the wake of the first cylinder. Phase 2, it happens that the wind direction has changed a little bit, or one of the cylinder has moved by a gust or so, a little bit outside of the symmetry line, and then the flow is flowing through the gap. And when the flow is through the gap, then a lift force, Fy, is generated. And this force, this crosswind force, pushes again back the cylinder into the phase 1 situation. Because it is vibrating, by inertia forces, it vibrates back, comes again to the phase 2 situation, and again the force occurred, and it gives also the pinch, pitch, pitch, and this is a self-excited vibration. And we called it interference galloping. The amplitude which can be generated may be very, very large. We have made model tests in this field, and we found out that there are very different case of, sorry, that is too low, too fast. Back again. Come on. No. So, left is a photo of 2 stacks on the University of Dortmund in Germany. You see the 2 cylinders, 2 stacks on behind the first one are vibrating in a galloping mode. And the right side, you see a model test. That is a plan view. The first is still, is in rest, and the rear side is vibrating with an amplitude of plus minus peak to peak 1 diameter. So this phenomenon was unknown at that time, and now it is known, and we have developed a calculation procedure for this procedure. Okay, now I come to a next point, rain, wind, vibration. Wind-induced vibration. What does it mean? The first time, I will say, we have observed vibrations on cable-stayed bridges, on the cables, and we couldn't explain why do they vibrate in such a large amplitude. Then I was in Japan in '83, and Professor Shirashi showed me a video. They had, at this time, built very large cable-stayed bridges in Japan from island to island. And he showed me a video with very large amplitudes of the cables. And he said to me, please, this is top secret, do not speak about it. Because the factory which built the bridges did not want that it was published. Later on, 4 years later, we had a conference in Aachen, and Mr. Shirashi's assistant, Mr. Hikami, presented then this phenomena. From this time, I could speak about it. So, what is it? What does it mean? The rain-wind-induced vibration, oh, sorry, that is too fast. Go back. Come on. Based on wind tunnel tests, we have investigated many situations, and I want to have the next figure. Yeah. What happens? You have the cable, it's a cylinder, and it's raining. The water is flowing down the cylinder and is on the lower side. Then there comes the wind. The wind is blowing and pushes the water upwards. And it occurs two rivulets, water rivulets, these black points there. But this situation is not symmetrical, depending on the direction of the wind. So you have a non-symmetrical pressure distribution on the cylinder. That causes crosswind forces, and the cylinder starts to move. And when it moves, then the rivulet are not stable. They moving up and down, and causes exciting forces, mostly across, but not only across, also in wind direction. And this is a self-exciting vibration, very dangerous. And now I see you in the video. That was a top secret video. I have it now. Come on. Oh, that is for model test. Okay, this is the video from the Japanese bridges. It's impressive, huh? This vibration, rain, wind-induced vibrations, it happens in low wind, not a strong wind, maybe 10 meters per second or so. It is not a problem, and this is a cable here on the foundation. The sound is not here. You can sound it, pok, 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 very heavy. Next one. This person tried to damp, he installed a rope, but it was not very successful. It was still vibrating. Okay. I believe you have an impression about wind-induced vibration. It is very, very interesting phenomena. So, I speak about vibration. Vibration is not a good situation in the civil engineering practice. You have to find a solution, And one solution is to increase the damping of the system. There are different types of damping. You can use direct damping if possible, and you can make aerodynamic devices. But the most successful device is the so-called dynamic vibration absorber. The dynamic vibration absorber is very well known. Back. Next one. It's very well known. It is based on the theory of Den Hartog. So, this is a principle. You have a main mass M1. That may be the stack, this may be the antenna mass, that may be a bridge. And you add a small mass M2 connected with a spring and a damper element. This left figure is for vertical vibration, the right figure is for horizontal vibration. It's the same principle. And this mass ratio, M2 to M1 to M2, is very small. Maybe 2%, 3%, 5%, maybe is the maximum. Some dampers have 10%, it's not necessary. 2-3% is general using. And there are many proposals for such a system on the market. And we have developed a so-called dynamic vibration absorber on the basis of liquid. Oh, das ist aber hier. This is called tuned liquid damper. Why does it work here? So, again, it is a liquid in a box. And the sloshing of the liquid is the second mass, M2. And the frequency of such sloshing mass can be calculated easily. In every physical books you can read it. But there's no information about the damping effect. And we have made intensive investigations about the damping effect. One of my co-workers has made his PhD about this point. And you see here an example. This is a video. On the upper figure, you see a box without liquid. And the same box on the lower part is with liquid. And now start the video, please. Can you start the video, please? Yeah. You see, the lower box after 2-3 amplitudes is in rest, and the upper one without liquid is vibrating. It's the same model, only put together in this figure together. It's a very effective damper system, and it is very cheap. It's only a box with water with a liquid, anti-freezing liquid, because in wintertime it can be frozen. And the only conditions it must be fulfilled is it must be the box must have no hole that the liquid can flow out. It must be very well welded. This is the only fiction, and you have no maintenance. You build it in the buildings or in the structure and in the stack, and you can forget it. We have started with this type for 20 years ago, and they are still working. That's a very simple system, and we use it very often for steel stacks. It's very often used. It is a round curve, a round tube with boxes, and it works very well. Thank you. So this is the vibration absorber. Now I have another point. You would have this problem with the sun on the buildings. Sunscreen is a word. The sunscreen for protecting the rooms against hot sun. If this sunscreen is outside of the facade, then you will have the problem, if the wind is coming up, will be destroyed. Then you must pull up. And the classical way is to have an anemometer on the top of the building or on the side, and then the anemometer says, oh, the wind is strong, then pull up. And all the sunscreens are pulled up. This is nonsense. On the other side, where the wind is not acting, you must not pull up. So therefore, we have developed a system that is called wind characteristic. The wind characteristic is the following. We measure in a wind tunnel the wind on the facade, on different points of the facade, and we receive a so-called wind characteristic. This is the left figure. The wind characteristic means this is the wind speed versus wind direction, normalized, of course. And you see here an example on a special point on the building. This is north, 0 degree is north. So we have then on the northwest direction, we have a high attack of the wind. Also on the east-south direction, but on the north side, on the north and the northwest, also on the south and southwest, you have less wind action. That means that at that point, only when the wind is coming from these directions, it would be pulled up, not on the other wind directions. On the right side, you see the anemometer. The anemometer is mostly on the top of the building. And on the top of the building, we use the best position. We want to have a homogeneously round curve for the anemometer. It's not possible in all points, but this is really, really good situation here. And this information is put into the computer. It's connected together. And then the computer, as a formula for this, a control formula, says, okay, when the wind comes from northwest, you pull up the facade on side A. The other sunscreen are remaining on the below position. So this is a very successful system. Wind characteristic method has been applied especially to very large buildings, and you spare energy, and you have a more comfort for the people. The next point what I will speak about is wind comfort. It is well known, and you enter or you approach a large building or a big complex, and the wind is blowing. There are special places or points where the wind is increased. You turn around the corner, suddenly you have a wind on your body. This is wind comfort. Here, three examples. Okay, 3 examples. You see here the wind situations where the wind may be large. And then this can be handled in a wind tunnel. You can find out the area where the wind is high, and then you can calculate the comfort with comfort criteria. Cleaning waste will be my last point. This has not directly to do with civil engineering, but I think it has to do in a special way. The waste gas on power plants, on motor cars and so on, is a problem, a discussion in Europe, and I think is a discussion in every country. And the problem is to clean the waste gas. And we have developed a mixing system for cleaning the waste gas for the NOx. It's a nutrient oxygen gas. It's a not very healthy, this gas. So to clean it, in the power plants, we have installed such a system, and it is based on a Vortex system. It's a so-called leading-edge Vortex system. This is here a model test, and when you put the ammonia, this is the ammonia must be injected into the waste gas. Ammonia and the NOx is cracked in the catalyst. It is installed in the cars, you know it. And we use it in power plants, and we have received removal rates of up to 97%. And the diesel cars, which are on the market, have a removal rate of 60% or 70%. So my proposal for the companies is to use our mixing system in order to increase the removal rate, and I hope they will do it in the future. And then the discussion about the NOx attack will be out of discussion. You can forget it. Okay, so this is my talk. Thank you for your attention.
Before introducing the next keynote speech, I would like, on behalf of the organizing committee, to express apology to the audience for not having the third keynote speaker here at this session, Professor Khalifa Al-Jabiri from the Sultanate of Oman, who was not given the permit to enter Palestine from the occupied Israeli authorities. His paper was regarding the compressed earth blocks as a sustainable material in the construction of cost-effective buildings. The next keynote speech is for Mr. Engineer Joseph McHenry. Mr. Joseph McHenry is a chartered engineer and a highly experienced senior power system professional who has managed and worked in the electrical transmission and distribution fields for nearly 30 years in Ireland and Oman in diverse areas such as distribution engineering, asset management, power system studies, network planning, and the integration of renewable technologies in distribution and transmission networks. He is an affiliate member of the Association of Chartered Certified Accountants with significant career experience in the areas of auditing, financing, and investment appraisal. He is a trained internal auditor and worked as a senior auditor in the internal audit department of Ireland's vertically integrated electricity company, carrying out independent appraisals for all company activities, reporting on the management of risk, adequacy of internal controls, and on the achievement of efficient, effective, and economic use of resources, project management, contractor management, technical objectives, change management, safety, financial reporting, variances, and value for money. He is a former senior manager of planning and asset management in MEDC. Okay. Where he developed the ISO certified asset management system and managed and ran the internal audit program of that system, which is a key requirement for the continued certification. Please, Mr. Joseph McHenry.
Thank you very much. Good morning, folks, and thank you very much to the organisers for inviting me to speak today and to present to you on renewable energy. So my talk today is around renewable energy, but particularly, I suppose, the challenges, just touching on some of the challenges that there are with large-scale integration of renewable energy onto power systems. This particular installation on the first slide of my presentation is actually a 500 kilowatt PV installation, solar PV installation in Deir, I think it's called Deir al-Bala in Gaza Strip, that I photographed when I was there last year. Okay, just an outline of the presentation, just a very brief look at my background in relation to renewable energy. The developments that there have been recently in relation to renewable technology and how they're changing the development of renewable technology on power systems. Some renewable economic trends that are also impacting on those changes. The technical challenges that there are to integrating a lot of renewables in power systems. We look at a European case study, and in this case we're going to look at Ireland, my own country, because there's a particular reason why Ireland is worth looking at. And then just look at the renewable potential in this region. So very quickly, just I'm a utility engineer, about 25 years in Ireland, around 5 years in Oman. And I've worked with a number of different renewable technologies in the development of their technology, particularly around marine renewable technologies. So one device was a wave dragon project, which was approximately a 4 megawatt overtopping device. So it was essentially a floating reservoir with a ramp, so the waves came up the ramp and generate electricity through low head turbines from the reservoir. I've worked with the CGen project. We'll see there's a photograph or an artist's impression of it later on in the presentation of the CGen device, which is a tidal stream device, and it was the largest such device in the world when it was installed in Ireland. And I've carried out feasibility studies into solar renewables in projects in Gaza, in Oman, and West Africa as well. Okay, so looking at some of the developments in wind technology, I suppose one of the major developments in wind is the turbines are becoming very much larger. The early commercial turbines might have been in the kilowatt range. Siemens and in fact GE, this particular one is on a GE turbine, are now looking at turbines that are over 12,000 kilowatts, so we're talking about 12 to 12.5 megawatt range. These are also fully non-synchronous. This is not something which I know electrical or mechanical and civil engineers probably have a whole lot of interest in, but this is changing the nature of technology, and I'll touch on it later, a brief overview of that. But they're becoming completely non-synchronous, which is good from the quality of the power they produce, but they do produce other problems. As wind has become a larger and larger part of power systems, in the early days they were given a free pass because they were very small on a large power system. They were largely allowed to behave as they kind of wanted to an extent, but increasingly they became an important part of power systems, so they couldn't and were not allowed by transition system operators to operate in that fashion anymore. So this is increasingly tight regulations on them and how they operate. We're seeing larger and larger wind parks connecting to the system, so the point of common coupling is becoming a larger export capacity. And also now we're starting to see a lot of offshore developments happening as well. And one of the interesting things about offshore actually is, firstly, the wind tends to be more predictable, and also, as we can see on the presentation here, I think if I have that, it doesn't work. The capacity factor here is going up to 63%, which is a very high capacity factor for wind. You know, that's nearly getting as good as some of the older thermal technologies. And also in this, there's a very significant per megawatt cost reduction. There's been very significant reductions in the cost of wind installations, largely because of economies of scale, but also of learning. In the solar PV area, really the major development in solar PV is a reduction in costs. You were talking about, values of around $76 per watt back in the 1970s to, this graph only goes up to 2015, but it's dropped further. There's been absolutely dramatic drop. I was doing a presentation on marine renewable technologies in ESB International around 10 years ago, and the solar PV was not reckonable at all as a grid scale technology at that point. So 10 years ago, it was simply not regarded as a possible technology for grid scale because it was just simply too expensive. That has completely changed. In the last 5 to 10 years, that has completely changed. There's also been a significant increase in solar PV efficiency. The monocrystalline PV is the best PV technology, and they're getting up at 23–24% now, which is a very good efficiency rate. But the polysilicon, which is a cheaper technology, is getting very good as well, and it's following behind the monocrystalline by only about 3–4%. So they're getting up to 20% efficiency on the polycrystalline panels now. And then there is a third major technology, which is called thin film technology. I've never actually worked with that myself, but that's a cheaper technology again, but its efficiency is lower. It's lower probably by about 6–7% than polysilicon. So where you have a lot of area and land is not at a premium, the thin film may be the better way to go. But in general, the cost per kilowatt is just dropped dramatically in the last, certainly in the last 10 years. The design of them, the technology design there can be converters from the DC to AC at the panel. There you can string a number of the panels together and have a converter on that, quite small ones, which is what we were looking at in the installation in Gaza. And then you can have the centralized converter designs as well. With the solar PV, to get maximum energy output, you generally have to have 2 axes tilting for the maximum output. So you're following the sun for both seasonal and the daily sun. But that tends to be quite expensive, so a lot in the earlier days tended to go for a single axis, which was following the sunlight throughout the season. However, the fixed tilt is becoming increasingly popular because the energy loss in the fixed tilt, and it was fixed tilt in the one that we saw there on the front, in the first slide. It's cheaper and the maintenance costs are easier and much lower, significantly lower. So increasingly, these large-scale, grid-scale solar PV farms are fixed tilt. Looking just quickly at other renewable technologies, I said to you that I'd worked on the CGen device, so that's the CGen device here. We see it was located up in Strangford Lough in Northern Ireland. It was 1.2 megawatts, so each of those 2 turbines was 600 kilowatt. There's very strong tidal currents in the Narrows in Strangford Lough at that point. That was a demonstration device. It was installed there to do it, and I propose and manage a number of contracts to support the technology developer, amongst which I did an entire project on the power quality assessment of the electrical power from this device, and we published a number of papers in engineering journals and conference proceedings. However, for tidal, it's still really unproven. That device is in very sheltered waters. How would such a device work out in the open ocean with large waves? These sort of issues still have to be teased out. Wave, likewise, is unproven, but the problem with wave and tidal remains it is very high cost in comparison to other renewable technologies. With biomass, it's a proven technology, but it's had much more modest growth, and there's been issues around challenges from the public and biomass plants, but in general, they've had much more modest growth. So largely, renewables today means wind or particularly solar PV in this region. The final element to do with technologies such as wind and solar is the notion of the whole area of energy storage. Because of the non-dispatchable nature of renewable, it's seen as a challenge, and indeed it is a challenge. It presents a challenge in power systems. So energy storage is really seen as key to putting them on a level playing field with the traditional thermal technologies. Really, to date, power system operators have used two energy storage techniques. Well, one in particular has been around for decades, and that's pump storage. You can see it up there on the top right of the graph. That's, in many power systems around the world have it. Ireland has a pump storage, which is a lower lake and a lake at the top of a mountain, and in the mountain is a number of turbines, and basically just by pumping the water to the upper lake, you store it, and then it's released through that. It's around a 250 megawatt pump storage facility in Ireland. Many other power systems around the world have them. They're not just used for energy storage, but they're used for operational flexibility of the power system, and it's extremely important in Ireland. So that's an old technology. It's been around since 50s, 60s. It's well known. It does not have great energy efficiency. The round-trip efficiency in pump storage is a little better than 50%. There's quite a lot of losses in hydraulic losses. The preferred technology would be batteries. They're much more efficient. They're much faster. Their round-trip efficiency is very good, well over 90%. However, cost remains really quite a significant challenge in relation to batteries, particularly at large scale, and we'll look at that later. There are other technologies that have been looked at, such as capacitors, flywheels, etc., but in the main, these are not particularly well developed. There's a number of demonstrator projects on that. So it remains a challenge area for renewables, is the whole area of energy storage. Okay, so looking now, this is from the Lazard. Lazard do a report every year looking at the costs of renewable technologies. And it really is quite eye-opening to look at these. If you look there, the fourth and fifth, you're looking at, well, particularly the fourth line, your crystalline utility scale. You're seeing there, you know, this is a cost it's dollars per megawatt hour cost. And you're looking, this is a lifetime cost, you're looking at $40 to $46. You compare that to something like a combined cycle gas, which would really be the most efficient on a life cycle basis technology at the moment. This would be combined cycle gas. You're talking about 41 to 74. So you're seeing a great cost comparison on a lifetime basis. This is made, and there's no subsidies in this at all. This is purely at a commercial cost. So you can see that certainly wind at 29 to 56, and you can see solar PV at 40 to 46 is very competitive now with some thermal technologies. Okay, there still are the challenges around the dispatchability, but it is still become very, very competitively costed. In fact, the competitiveness of the costing is so good that actually the lifetime costs of the likes of wind and solar, which essentially have a zero marginal cost because there is no fuel cost to them, their lifetime cost is cheaper than some of the traditional fossil fuels' marginal cost, which is mainly its fuel cost. So it has become extremely cost competitive, and this is one of the big drivers. So a lot of people think that renewables are driven purely by subsidy, and subsidy has driven a lot of renewable development, but it's not only that. Going back to batteries, Lazard also in their cost of energy storage report, we can see here in the number 3 down there, the utility scale, so that's PV plus storage. So looking at a solar PV plus storage, where before we were on 40 to 46, I think the numbers were, here we're now talking about 108 to 140. So we can see now that the costs are significantly greater once we add the energy storage element into it. And look at another challenge in a second now in another presentation. But so that just demonstrates again that we still have a commercial challenge around the energy storage element. Okay, now moving to some of the challenges that we have. Just checking the time. Just some of the challenges we have. This is a timeline, a logarithmic timeline, going from microseconds up to 1 hour. And essentially, power system engineers have to think about, when they're designing and operating power systems, have to look at this entire timeline. So when we're down at microseconds, we're at various wave phenomena, such as lightning-induced transients and switching-induced transients. Then from 1 millisecond up to 1 second, we're into electromagnetic transients, and then electromechanical transients, then from 1 second up to 10 seconds. You can see then we have POR, SOR, these are all the various reserves, and these are the types of issues that operators of grids have got to be thinking about the whole time and setting up all of these various reserves. Some of them, obviously, with the timescales they're operating in, are automatic, and others are dispatchable. So anything generally greater than about 15 minutes, you're into generation dispatch. But in fact, it's not even 1 hour. That graph continues on outwards into days, into seasons, years and decades. If you're looking at energy policy, you'll be looking out at decades in the planning of the entire power system. So what we're looking at now, some of the challenges of renewables are really around this area where there's the POR, SOR. It's this area from kind of 1 second up to about 15 minutes. They present challenges for us power system engineers that we're working to overcome. Okay, in a traditional power system, which power system engineers have known for about 100 years, you essentially had a grid and you have a number, not a particularly large number, but a medium number of large turbines connected to it. These are generally high-speed turbines. You can see somebody working on one here, the size of them. So these are spinning at high speed. What that means is you have a lot of mechanical energy, kinetic energy in the system in those large turbines. Okay? Now the advantage of that kinetic energy is it helps with the system frequency control. Here's showing an analogy that you have generation going into a reservoir and you have demand coming out of it. The bigger that reservoir, the less the level in that reservoir will change if there's any change to the generation or any change to the demand. The smaller that container becomes, the more that level will move up and down. Ireland has studied this, and I'll show shortly why. Ireland is ahead of the curve in terms of having to deal with these issues. But this has become really the #1 technical constraint, is the stability of the frequency on the system. The more we take these traditional old generators off and put instead on those new wind turbines and solar PV, we're losing this system inertia, which means we can't control the frequency as well as we did. And that's the big challenge. They've studied all the other areas, most of the others are solvable. This is solvable too, but we have to come up with new techniques to manage it. Okay, to indicate why the likes of wind and solar present problems for us, typically when you're looking at the output of a solar PV, you'll see a graph like this. Now normally it is a nice, even shape. But in reality, when you're looking at it at intervals of every quarter second or so, this is really what you're looking at. You're looking at large drops in output from time to time. That's fine if it's only small on a large system, but if it's a significant part of the system, this presents a huge challenge because suddenly you're losing a large part of your generation. It's not untypical for these solar PV to drop 90% of their output in less than a minute, and they can do that a couple of times a year. That's a problem. So they're going to have to put on some sort of smoothing onto them. So for the likes of a 40 megawatt solar PV installation, it may well have to have 20 megawatts with 4 megawatt hours of storage in it just to do the smoothing. Because typically utilities don't like to see the output change, the ramping down of the generation by more than 10% per minute. That would be a typical sort of limit that utility operators want. Wind is a little different. The bigger issue with wind is the forecastability, but it does drop quite dramatically, but not in the same way that solar PV does. So there is there's very high variability in wind, and there's a very short forecast horizon. Showing in a graph here for a recent day in Ireland, you can see in the green, the smoother, darker green is the forecast wind, and the one with more volatility on it is the actual. And you can see there's significant variations between them of at least a couple of hundred megawatts. So this presents a challenge for dispatchers in arranging the power on the system. Another constraint that arises in the system is network constraints. Typically, renewables are placed in areas where there's much less people, you need space. It also tends to be in mountainous areas where people aren't living. That means the grid tends to be quite weak in those areas. So you can end up with network constraints when the wind is blowing strongly or there's good sunshine. It can present network constraints, particularly more for wind than it does for solar. Okay, so looking at the wind target figures, the important thing here is Ireland and Britain are separate from Europe. They're not just islands, but from an electrical perspective, they're separate from Europe. Continental Europe is a single synchronous grid. The island of Britain is a single synchronous grid, and the island of Ireland is a single synchronous grid. They are connected to one another, but by DC connectors. This is important because each synchronous unit has to manage these issues on its own, okay? And that's why I said Ireland is ahead of the curve. Even though the amount of wind we have is less than, say, the likes of Germany or Denmark, it's much higher compared to the size of the system. And that's why we've got ahead. And even at recent industry events in Ireland, I've noticed Japanese engineers are now coming over to see what we're doing in Ireland, because Ireland's having to deal with these issues far ahead of other countries. So the target for Ireland is 37% by 2020. We'll look shortly at the figures, but we're close to that for 2018. So the Irish grid here, you can see a quick map of it. It's a single all-Ireland grid, Northern Ireland, the Republic of Ireland, and there are two approximately 500 megawatt DC interconnectors to Britain and a proposed one now to France being looked at. There's about 5 gigawatt of wind on the system, and there is effectively no solar PV. So the wind power in Ireland has supplied 33% of electrical energy requirements in Ireland in 2018. You see here in the wind dispatch, it's gone up to as high as 4,000 megawatts, the wind. But you can see there in the orange where it has to dispatch down because there's too much wind on the system, and this is to do with the frequency stability. The key metric here is this one, SNSP, System Non-Synchronous Penetration, and they allow up to 65%, which is basically wind and those two DC interconnectors. They allow up to 65% of the load at a particular point in time, but the target is to go to 75%. Now this is well ahead of any other large synchronous system. And a whole new suite of tools and instability indicators and real-time tools and training for the system operators had to happen. But you can see here in the bottom graph, this is indicating that they're intending to go to 75%, and at that point they will evaluate it and they may try and go further. Just looking very quickly at the solar resource here from a World Bank resource map, you can see here for this region, this region is one of the better solar regions of the world. And looking at the wind resource, you see this is not one of the better regions in the world for the wind resource, but you can see the likes of Ireland and Britain and other parts of the world are very good for the wind as a resource, and that's why wind is such a strong renewable in Ireland. So looking at a solar PV, 7 megawatt peak in Gaza, you can see here on the graph, once again showing that smooth graph of its hourly output. You can see the variation between summer and winter in it. But a 7 megawatt peak would produce about 12,500 megawatt hours, which on the basis of 3,000 kilowatt hours per household will be about 1.1% of Gazan electricity demand, but gas and electricity demand is lower than that assumed figure. It's lower than 3,000, so it probably is more like 3 to 4% of gas and electricity demand. So, and that's just for a single solar PV installation looked at in the access restricted area in northern Gaza beside the wastewater treatment plant. The levelized lifetime cost of electricity from that facility would be about 5 US cents per unit of electricity, which is very good. It's a very good cost. So Gaza already has one 500 kilowatt installation. Obviously it has plenty of domestic, but at the grid scale, only one that I'm aware of. There is tendering underway for a 6 megawatt peak up beside the wastewater treatment plant. There's a possibility of another 7 megawatt. So there's potential interest in the use of the ARA because land obviously is at a premium in Gaza. However, the networks are weak, so curtailment and constraining issues are likely to predominate. What's the potential in the region? Well, neighbouring countries are currently producing up to 4.5–5% of their electricity demand from renewables. And there's a lot more potential for them to add. So that's the sort of potential that exists here for Palestine. I think given costs and the resources here, wind is not likely to feature too much. I think it will be predominantly solar PV. But I think there's a great opportunity to learn from other regions on their development and the technical issues that they had and any other technical solutions that they have adopted to successfully integrate large-scale renewables into their power systems. Thank you very much.
لضيق الوقت مش رايحين نسأل ناخذ أسئلة. في حدا عنده ملاحظات بحب يحكيها؟ That's it. خلاص. شكرا. Thank you very much, Engineer Joseph McHenry, and see you in the next sessions. خلاص ايش؟ بنطلع لكوفي بريك هلا، وبعديها في السيشنز المتوازية في القاعتين اللي فوق، وفي الجلسة الختامية بنكون هون.